Well, welcome everybody, and welcome to yet another one of our online webinars. I think this might actually be the 20th one, but don't take my word for that. Okay, so this afternoon we have something which is not quite so chemical as we usually have, but it's an incredibly interesting subject. It's the subject of insulin, and of course, it's the centenary of the discovery of insulin, but I dare say Kersten will put a fight on that, possibly. So, welcome, Kersten. Thank you for coming to talk to us. And over to you on the subject of insulin, the crooked timber.
Okay, thanks very much, Peter, for that introduction, and thanks to you all for tuning in this afternoon. I hope I don't disappoint, because you know what, I am going to try and get a little bit chemical. I thought it's the Royal Society of Chemistry Historical Group. We've got to try and get this a bit chemical, so I will try and do that. So as Peter said, what I'm going to talk about this afternoon is insulin, the crooked timber, from thick brown muck to Wall Street gold, which is the title of a new book that I've just had published by Oxford University Press to mark the centenary of the discovery of insulin. But you know, this book actually began life with another book. This just illustrates the route we're going to take here this afternoon. Here's the thick brown muck as insulin was described when it was first used on human patients back in the early 1920s. Nearly 6 decades later, it was causing excitement again, but at that time it wasn't doctors, it was traders on Wall Street. And I will explain why shortly. But as I said, this book began its life with another book. So about 10 years ago, I was writing a book called The Man in the Monkey Nut Coat, and it was about this character here on the right, the physicist William Astbury, who will be appearing in this talk later on. So that's why I'm flagging him up now. And it told the story of how, thanks to his work on the structure of protein fibers in wool, he helped weave a path to the discovery of the DNA double helix. Now, anyone who's done any writing, I think, will confirm that writing can be an absolute exhilarating process. It can be an absolute joy, but it can also leave you very tired and very grumpy. And while I was writing Man in the Monkey Nut Coat, I noticed I was becoming a lot more tired and grumpy than usual. And my first reaction to that was, dare I say, a typically male one. I basically just shrugged those symptoms off and dismissed them as being nothing more than just inevitable traits of a man in middle age. But then a few more symptoms began to manifest themselves, and that is what started ringing alarm bells that something far more sinister than just middle age might be going on. I found vague memories of very distant undergraduate lectures in metabolic diseases stirring. And as a result of that, I took myself off to my GP, and I watched as my GP tested a sample I brought, and I saw the look of utter horror come over my GP's face, because basically there was that much sugar in my blood. My blood had basically turned into treacle. I think my blood sugar was at something like 33 millimolar when it's supposed to be between 4 to 6 millimolar. So I was packed off to St. James's Hospital the minute I left the GP surgery. Turned out my body was producing ketones. I'm guessing, it's being the Royal Society of Chemistry, no need to tell anybody that that's bad news. In a very short space of time, they would have put me into a ketoacidotic coma and I would have been dead. And in a nutshell, I'd basically developed type 1 diabetes. So what I'm going to talk about today is the discovery of insulin, because prior to the discovery of insulin, a diagnosis like that, like I had, would have been a death sentence. So before we launch into insulin, we maybe just need to have a little bit of a recap about what insulin does and what's going wrong in type 1 diabetes. So I'm figuring, you know, it's 2 o'clock in the afternoon. We've probably all had our lunch, or maybe not, depending on where we are in the world. If that's the case, we might have eaten potatoes, bread, pasta, rice. All those things contain carbohydrates, and Carbohydrates are great big long chains of sugar molecules bonded together. So right now in our digestive systems, the links between those sugar molecules will be getting broken down, and the simple sugars will be passing into the blood, where they'll be then transported around the body to be used by tissues like muscles as fuel. Now, to get out of the blood into those tissues where the sugar is needed as fuel, the sugar needs the action of the hormone insulin. And insulin's made by these little patches of cells called the islet cells that are in the pancreas that sits just under the stomach. So that's what's happening in a healthy person. What had gone wrong with me, for reasons we don't understand, is that my own immune system had actually turned on these islet cells and started to destroy them. So if the islet cells are destroyed, there's no more insulin. And without insulin, the sugar can't get from the blood into the tissues where it's needed. And that causes a number of symptoms. Typically, what is probably the most common and well-recognized symptom of the onset of diabetes, it was certainly known as far back as the ancient Egyptians. There's a scroll, it's about 3,000 years old, the Ebers Papyrus, because it was found by German Egyptologist Georg Ebers in the 19th century. And it writes of a medicine to drive away the passing of too much urine. And that comes about basically because the level of sugar in the blood is so high that the kidneys are going into overdrive to clear all this sugar out of the blood. In fact, that's where diabetes gets its name from. It was the 2nd century Common Era physician Areteus who actually coined the term diabetes, takes its derivation from the ancient Greek word meaning to siphon or to flow. But I think if a prize was going to go to the most memorable, vivid and colourful name for diabetes on the basis of this symptom, it would have to go to the 18th century physician, Thomas Willis, who referred to diabetes thus. I'll just let you see his very colourful title for diabetes there. Well, of course, frequent trips to the bathroom are possibly the least of your problems as a type 1 diabetic patient, because while sugar may be sweet, it can also be pretty nasty stuff when it's in high concentration. So over prolonged periods of time, elevated blood sugar levels will damage the retina at the back of the eye. But to believe that, that diabetes is the biggest cause of blindness in the UK, I think. Eventually, the kidneys will fail. High blood sugar levels cause nerve damage, increased risk of cardiovascular disease, stroke, and increased risk of infections, which has been particularly of concern during the recent COVID pandemic. And of course, on top of all this, what will happen is, because your body can't metabolize the sugar from your diet, it has to turn to alternative fuel sources. So you start metabolizing protein and fat. That leads to the production of ketones, and these will acidify the blood and put you into a fatal coma. And before the discovery of insulin, that was the fate, sadly, of every diabetic patient. The best that could be done was to put you on a starvation diet to delay the inevitable. So little wonder then, when insulin was first discovered, diabetes specialists were absolutely delighted. Here's one of them, chap here on the left, Elliot Jocelyn. He was so stunned by the power of insulin to pull his patients back from the brink of death. He found himself comparing it to the vision of Ezekiel. So Ezekiel being the prophet in the Old Testament who is said to have seen a valley of dry bones rise up, be clothed in flesh and restored to life. And for Jocelyn, insulin was the vision of Ezekiel. It was having this power on his patients. Surprisingly, one person who you might expect to have been really delighted was the person who's credited with the discovery of insulin, the Canadian scientist here, Fred Banting. Now, I think that getting the phone call that tells you you've just won the Nobel Prize must be the phone call that every scientist secretly dreams of receiving. And one morning in October 1923, that dream came true for Fred Banting here. But his reaction was not what you might have expected. He was absolutely furious. A friend had rung him and said, "Have you seen the morning newspaper?" Banting said no. So the friend told him the news: "You've just been awarded the Nobel Prize 1923 for physiology or medicine for the discovery of insulin." Banting was livid. He told his friend to go to hell. He slammed down the receiver, checked the morning newspaper. Yes, it was true. Then he jumped into his car and he drove across Toronto in an absolute fit of rage. Why was he so angry? Well, here's the answer in this newspaper clipping. So as you can see there, Toronto doctors honoured. There's Banting on the left, Nobel Prize to Banting. And then in smaller print underneath, Dr. J.J.R. McLeod also. McLeod is the gentleman on the right. He was professor of physiology at the University of Toronto. He was also Banting's boss, and Banting hated him. Banting loathed McLeod with a passion, and he thought the issue he had was that the Nobel Prize not just been awarded to Banting, he'd had to share it with McLeod, and he thought that McLeod had no right whatsoever to have any share of the credit for the discovery of insulin. Now, I think that's a little bit harsh on McLeod, because had it not been for McLeod, Banting would never have done that work in the first place. Banting had come back from serving on the Western Front in the First World War, where he'd been in the medical corps. He'd been wounded, decorated for courage under fire. He'd come back to Toronto to Ontario rather, with high hopes of setting himself up in a private medical practice. But things didn't work out, and his career was going rapidly downhill. He had no patience. So to make ends meet, he began doing a little bit of teaching of university students. And one night before bed, he was preparing some lectures, and he went to bed with a paper all about the pancreas. And that gave him an idea for trying to find insulin. Now, where we were at this point was, in the 19th century, it became evident that the pancreas was somehow involved in diabetes, and that led to speculation that maybe the pancreas is producing a chemical messenger, a hormone that regulates blood sugar. So the hunt was on to try and find this hormone. And with his piece of bedtime reading there, Banting thought that he had glimpsed a novel way that that could be done. So he took his idea to McLeod. Now, McLeod was cautious. He didn't really believe that Banting had sufficient surgical expertise to be able to carry out the experiments he was proposing. But nevertheless, he gave him the benefit of the doubt. So he gave Banting some lab space, and he fixed him up with Charles Best here on the left, who was a final year honours student. And during the summer of 1921, Banting and Best began working in the sweltering Toronto heat in this laboratory to try and find insulin. And the way they did that was, their experimental plan was basically they were going to surgically remove the pancreas from a dog, so the animal became diabetic. And then they were going to make pancreatic extract from the pancreas of a second dog and inject that extract into the diabetic animal to see if the pancreatic extract would bring the diabetic animal's blood sugars down. Now, there's a lot of mythology has grown up around these early experiments. It's a very mythologized telling that goes something along the lines of, during the summer of 1921, these two young, inexperienced researchers triumphed against all the odds while their boss, McLeod, was away on a fishing holiday in Europe, and they came up with this miracle cure. Well, the late, great Canadian historian Michael Bliss was the first person to really go back and study Banting and Best's original notebooks, and he pretty much comprehensively demolished that mythologized account in his wonderful 1982 book, The Discovery of Insulin. Bliss showed a lot of those early experiments were unreliable, they were inconsistent, they were poorly controlled, all of which was pointed out to them by their boss McLeod in a series of correspondences with them while he was away on his fishing trip. And I guess McLeod was just acting as a responsible supervisor should, but Banting took this all the wrong way. He was becoming convinced that McLeod was out to steal his thunder for the work on insulin. And things came to a head at the end of 1921, because by that time, McLeod felt it was time for Banting and Best to present their work formally to a scientific audience, a scientific meeting. So they all traveled down to the University of Yale, where in front of the great and the good of North American diabetes research, Banting was going to get up and present their work, which he did, and it was a complete disaster. The prestige of the audience, all these great luminaries in North American diabetes research, took its toll on Banting's nerves. He stood up and he was paralyzed with fear. The words just would not come. MacLeod is sitting there in the audience, and he's basically looking at defeat being snatched from the jaws of victory. And he realizes he's got to do something. So he stood up and he took over Banting's presentation. Again, he probably thought he was doing that because that's what a responsible supervisor does. Banting saw it very differently. For Banting, this was nothing less than a brazen coup by MacLeod to steal his work, and worse than that, he'd had the gall to do it in front of the North American diabetes community. It confirmed all Banting's festering fears that MacLeod was out to steal insulin. And Banting realized he was so fearful insulin was slipping from his grasp. He realized that what he needed to do was to do something that would stamp his name on this discovery. And in early 1922, the opportunity came to do just that. So in the middle here, we've got Leonard Thompson, who's a 14-year-old boy. He'd been diagnosed with type 1 diabetes a few years earlier, in 1919. When his father brought him into Toronto General Hospital, he was at death's door from type 1 diabetes. His weight was down to 65 pounds. His hair was falling out. He stank of acetone. On the 11th of January, 1922, Leonard here was injected with some pancreatic extract prepared from bovine pancreas by Banting and Best. And it was not a success. Sure, Leonard's blood sugar levels came down, but he still carried on producing ketones. And more seriously than that, he suffered an adverse toxic reaction. He came out in abscesses. And that was a response to toxic impurities in the pancreatic extract, because these were very crude extracts. And when Banting and Best even wrote this work up for formal publication, they quite bluntly said no clinical benefit was evident. So it's quite interesting that just over a month ago, much was being made of this, of the centenary of this date, the 11th of January, the first time a human patient was injected with insulin. Well, it's true, but it wasn't a success. 2 weeks later, on the 23rd of January 1922, Leonard was injected again. This time it was a success. His blood sugar levels came down, there was no production of ketones, and most crucially of all, there was no toxic reaction. So what had changed in those 2 weeks? Well, what had changed was that second batch of extract hadn't been made by Banting and Best, it had been made by their colleague, a guy called James Collip, who joined the team in late 1921 from Alberta. He was a biochemist by training. And what Collip had cracked was that you could use alcohol to clean up these extracts, to remove those toxic impurities and to precipitate out the active agent. And to be fair, Banting and Best had been trying to use alcohol, but it was Collip who really cracked how to do it. And as a result of that, a few months later, May 1922, MacLeod got up at a meeting in Washington, DC, and made the first public announcement of the discovery of insulin. And so the accolades began to flow in for Banting. He received an annuity from the Canadian government. He received an invitation from King George V to come and have tea at Buckingham Palace. And then, of course, a year later, he gets the biggest accolade of all, the Nobel Prize. And he's furious. And he's not the only one. Because over in Germany, poor old Georg Sulzer here, a clinician, looked on in utter fury and dismay as he saw the Nobel go to Banting and MacLeod, because as far as Sulzer was concerned, he'd already discovered insulin back in 1908. He'd made a pancreatic extract. He'd recognized that you would need alcohol to remove impurities that might cause side effects. And he tested it with some degree of success on patients in Berlin hospitals. He'd even had the support of pharmaceutical giant Hoffmann La Roche. And by 1914, he had a potent preparation of insulin. And then, of course, the outbreak of the First World War, and that brought all his work on insulin to an abrupt halt. And it has been speculated that had that not happened, he might well have been looking at the Nobel Prize. So why then do we not remember the name of Zeltzer? Why is it that when Jeremy Paxman on the recent Christmas edition of University Challenge asks, name the discoverers of insulin, the correct answer is buzzed back in as Fred Banting and Charles Best? Well, that might have something to do with someone else who was mightily put out by the award of the Nobel Prize to Banting, and that was his lab partner, Charles Best. Now, Banting always felt guilty that Best hadn't shared the Nobel Prize, so he publicly divided his share of the prize money with Best. If he was hoping that would pacify Best, he was mistaken, because over the years, as Banting began to collect more and more accolades, Best looked on with increasing resent. Banting had a research institute named after him. Best wanted similar. And the relationship between the two men began to unravel and turn sour. So much so that in early 1941, Banting boarded a top secret wartime flight to Great Britain. And shortly before boarding the plane, he is alleged to have said, this mission is risky. If I don't come back and they give my chair to that little, well, you can see his particular adjective that he used there for Best, I'll never rest in my grave. But he could never have realized how tragically fateful those words would prove to be, because shortly after takeoff from an airfield in Newfoundland, the plane developed engine trouble. The pilot realized they were never going to make it across the Atlantic, so he had to turn the plane around, make a crash landing in which Banting was killed. Now, MacLeod was already dead. He died in 1935. So of that original Toronto team of 4, there were now only 2 members, Charles Best and James Collip. And Charles Best was damn sure which of those 2 names the world was going to remember for the discovery of insulin. Because as Best's star began to rise through the North American medical establishment, he began to give a number of prestigious addresses. And in that, he did something very interesting. He made the point of diminishing the role of James Collip. Another strategy he had was he co-authored a textbook of physiology for medical students. It's actually still in use today, Best and Taylor. But in a very early edition, the passage about the discovery of insulin is very, very revealing, because Best makes it quite clear that it was he and Banting in the summer of 1921, and that the efforts of people like Zeltzer were only marginal. Now, if Best was hoping to achieve scientific immortality through the pages of a scientific textbook, he would have been very disappointed, I think, to come across one very popular undergraduate biochemistry textbook that, as recently as the 2011 edition, if you look at the section on insulin, the discovery of insulin is credited not to Frederick Banting and Charles Best, but to Frederick Banting and George Best. When I first came across that conjured up an image that was so hilariously surreal in my mind. I think it took me about 5 minutes to recover from incapacitating laughter in the medical library here at the University of Leeds, and I got some very odd looks from the librarians. But nevertheless, as I said, Best worked hard to diminish the contribution of Collip. So the challenge before Best was this: when do you say that insulin was discovered? Is it the summer of 1921, when you found a pancreatic extract that will have an anti-diabetic effect in a dog? Or is it January 1922, when you've got a pancreatic extract that will exert an anti-diabetic effect in a human patient? If you go for this one, January 1922, you've got a problem. Because you've got the contribution of Collip, you've got the fact that that first injection on the 11th of January using the preparation by Banting and Best wasn't a success. Now, Best tended to make out as if that was the key date. But over time, people began to wake up to Collip's contribution and say, well, hang on a minute, wasn't it Collip's extract administered on the 23rd that really saved Leonard Thompson? The response to that was to then say, no, the real moment of discovery was that summer when Banting and I were doing the work on the dogs and Collip was nowhere in sight. Now, that might well have worked had it not been for a little inconvenient fact, and that was this: that in that very same summer of 1921, someone else had done almost identical experiments with dogs, and they'd done them better, and they'd published them in peer-reviewed scientific journals. That someone else was this researcher here, Nicolae Popescu. He was working in Romania. To his dying day, Popescu maintained that he was the rightful discoverer of insulin, and he craved the international recognition that he felt he deserved for that. Today, Popescu's name is known, but it's not really for the discovery of insulin, because relatively recently, the International Diabetes Federation were set to honor him with a bust and an honorary lecture. This is back in 2003, when suddenly some revelations came to light that caused them to call off all those events. And those revelations were the discovery that Popescu had also been a politician, a very extremist politician with vile and odious views. He was a founder member of a number of violently nationalistic anti-Semitic organizations in Romania that espoused violence against the Jewish minority, and his political writings are said to have played a role in inciting the Holocaust in Romania. And for that reason, the International Diabetes Federation came to the conclusion that while they would acknowledge he did have a role in the discovery of insulin, they were not going to celebrate this guy. So I've given you a little flavor there of the controversies around the discovery of insulin, but you know, there is more to the story of insulin than just its discovery. As I said at the start, when it was first discovered, it's been injected into patients, but chemically, nobody knew what this stuff was. Elliot Jocelyn described it as the vision of Ezekiel. His colleague Walter Campbell was equally impressed, but much less poetic. He described it as just 15 cc's of thick brown muck. And as I said at the start, 6 decades later, insulin's getting people excited again. This time it's traders on Wall Street, because when the bell was rung on the morning of the 14th of October, 1980, to commence that day's trading, dealers dived into a feeding frenzy like piranhas for shares in a newly issued stock in a little fledgling biotech company called Genentech. Apparently the shares began trading at $35. They rocketed up to $89. End of that first day's trade, they'd closed at $71 in what was then said to be the most spectacular debut in stock market history. Certainly by the end of that day, the two founders of Genentech, venture capitalist Bob Swanson here on the left, and Herb, molecular biologist at University of California, San Francisco, Herb Boyer here on the right, whose collaboration had begun when Swanson had initially rung Boyer up with the idea of setting up a company. Boyer had said, yeah, well, I can give you 10 minutes on a Friday afternoon. I think he's probably glad that he gave Swanson those 10 minutes. By the end of that day, first day's trading, these two were multimillionaires. And the legend has it that Boyer went out and bought himself a Porsche at the end of that first day's trading. Some have said he should have got the Nobel Prize. I like to think he maybe reflected on just how much happiness the Nobel Prize brought Fred Banting and concluded maybe he was better off with his shiny new Porsche. It landed Boyer on the front of Time magazine. So what was it then that the Genentech scientists had done? Well, basically what they'd done is, ever since the time of Banting and Best, type 1 diabetic patients have been having to manage their condition by injecting themselves with insulin from cows or pigs, from bovine or porcine pancreas recovered from abattoirs. Now, thanks to Genentech, they could inject themselves with human insulin, but it hadn't come from a human pancreas. It had been made by a genetically engineered bacterium, a bacterium that had had the genetic instructions that tell a human pancreas cell how to make insulin inserted into its own DNA. Now, there are a lot of unsung heroes in the story of insulin. I think there's one particular, very unlikely and unsung hero upon which Genentech's achievement was built. And here it is, the humble sheep, or rather, it's wool. So how on earth did that come about? Well, to understand that, let's just take a little detour into outer space. So a few years back in 2016, scientists at the European Space Agency got very excited when the Rosetta probe detected traces on a distant comet of a little compound shown here. It's called glycine. And again, I'm very conscious of the fact I'm addressing the Royal Society of Chemistry audience here, so I'm guessing I probably don't need to tell people what an amino acid is, but glycine is, I will anyway, glycine is a member of a type of chemical called amino acids. There's about 20 different naturally occurring amino acids. And the reason for the excitement among those space scientists is amino acids are the building blocks of proteins. And far from just being an essential dietary requirement, proteins are nature's nano machines. They are the workhorses of living cells. So hemoglobin, the stuff that carries oxygen around our blood and makes our blood red, is a protein. Rhodopsin in the back of the eye that converts photons of light energy into the electrical energy of a nervous impulse is a protein. All the enzymes that catalyze thousands of different reactions in our bodies are all proteins. What was known back in the 20s and 30s was that proteins are made of amino acids, but nobody could figure out how, because it was known that proteins in molecular terms were huge. They were great juggernauts, and yet these amino acids were small. So how did these little amino acids come together to form proteins? And that is where the humble wool fiber offered an answer. Thanks to the gentleman we met right at the start, subject of my book, The Man in the Monkey Nut Coat, physicist William Astbury. He had come to Leeds in 1928 to make X-ray studies of the proteins in wool, to study their molecular structure. And what he showed from that was that the keratin proteins that make up wool are great big long chains of amino acids linked together, a little bit like, if you imagine the amino acids being like beads of different shapes, sizes and colors, and they're all linked together to make a great big long molecular necklace that is the protein. Now, that in turn, I should say here, Astbury's finding was wittily summarized by a crystallographer and mathematician, Lindo Patterson. Amino acids in chains are the cause, so the X-ray explains, of the stretching of wool and its strength when you pull, and show why it shrinks when it rains. And it's to be hoped that Lindo Patterson didn't give up the day job of being a mathematician and crystallographer in favor of poetry. Okay, so proteins are long chains of amino acids. That raises another question. Are those amino acids arranged, those beads, those chemical beads on the necklace, if you like, are they arranged in any particular order? Well, already Astbury thought his work on wool had given him a glimpse of an answer. He was convinced that amino acids are arranged in nice, neat, regular, repeating mathematical patterns. You've got to understand, he was a physicist by background, and his passion was biology. But what he craved to find underneath the messiness of biology was the kind of neat mathematical regularities that physicists love. And he had a lot of support from two other big Goliaths of protein chemistry, Max Bergman here on the left and Carl Neiman at the Rockefeller. On the basis of precipitation analysis that they'd done of a few proteins like gelatin, collagen, albumin, they too had concluded that amino acids are arranged in regular repeating patterns. So just to give you an illustration, I've just shown a simplified example. Imagine we've got a protein here made up of only 3 different types of amino acid. What these guys are proposing is those amino acids are arranged in a nice repeat: dark blue, light blue, red, dark blue, light blue, red. However, there were dissenters. If these were the Goliaths of this story, here was the David on the right. Young-faced chap there, Richard Singh. Singh was a PhD biochemist at Cambridge. His work was funded by the International Wool Secretariat, and the subject of his PhD was to find a new method of separating and analysing the amino acids in wool. And from the opening pages of his thesis, he made it quite clear that he disagreed with people like Astbury, Bergman and Neiman. He thought the methods of analysis they'd used didn't have the precision or the accuracy to justify these grand claims about protein structure, and he was out to prove them wrong. So he teamed up at Cambridge with the chap on the left here, Archer Martin. Now, ever since he'd been a boy, Archer Martin had a rather unusual hobby. I guess it's not unusual for teenagers to spend long hours locked away behind their bedroom doors and their parents to worry about what they might be up to in there. Martin was no exception, but his parents really could have relaxed if they'd known what he was doing in the basement of his North London home. He was welding together Coke tins, old tin cans, and filling them with Coke powder of the black variety, not the white variety. Otherwise, I guess his parents would indeed have had something to worry about. The reason he was doing that was his passion was chemistry, particularly physical chemistry, the chemistry of separation systems. So whilst a researcher at Cambridge, he had built a machine that used a counter current flow system to separate vitamin E. And it was realized this was exactly what Singh could use for his analysis of wool fibers. But the best place to do that was not down in Cambridge. It was at the heart of the wool industry, a couple of 100 miles north, up in Leeds, which is why here up in Leeds in our department, we like to think of Martin and Singh as being the other great Leeds M&S story, besides a famous high street retailer. So Martin and Singh brought their work up to Leeds, because ever since the monks at Kirkstall Abbey and Leeds Centre had raised sheep and sold their fleeces to wool merchants, wool had been the economic lifeblood of Leeds, and it's for that reason Leeds was the headquarters of the technical site for a body called the Wool Industries Research Association, WIRA, which was sited in a lovely old Victorian house just about 2 miles down the road from where I live. The house was called Torridon. Sadly, it was knocked down in the 60s and replaced with a concrete and glass monstrosity. All that remains of the original Torridon site today is this gatepost. I think you might be able to make out the word Torridon there. And this old ruin, which used to be a stable, but back in 1941, this was actually the lab where Martin and Singh were doing their work. So you've got a picture of the two of them in here, sitting for hours on end in this lab that was filling up with chloroform fumes leaking from the apparatus, so that when one came to relieve the other, after a 4-hour shift, he'd find himself on the stream of a string of expletives from his colleague due to chloroform intoxication. So they were no doubt relieved to realize that actually this whole separation process could be simplified. You didn't need this great big machine to do it. You could still do it based on using 2 solvents, but simply do it using filter paper. So let me just move that out of the way and we'll change the slide over. And there's an example. So basically what they had done is they'd made a more sophisticated method of chromatography. They called it partition chromatography because it relied on the amino acids. So basically you take wool fibers, you break the links between the amino acids with acid, and then you run them out in 2 different solvents and they separate according to solubility. When they first showed that this could successfully be used on filter paper, their colleague there, Raphael Consden, is said to exclaim, "Behold, the Lord cometh." Well, Consden's excitement stood in sharp contrast to the rest of the scientific world. Because when Martin and Singh first presented partition chromatography to a meeting of the Biochemical Society in 1941, Martin recalled that it raised not a flicker of interest. Nobody took any notice. One person who was actually very excited by it was William Asprey, who we met earlier, because Asprey was convinced that partition chromatography would clinch his idea, it would prove his idea that amino acids are arranged in nice, neat, regular patterns in proteins. And he thought keratin in wool was a very simple protein. He thought it consisted just of 2 alternating different amino acids. Now, Martin realized there's a really simple way to test that hypothesis. Basically, you partially digest the protein necklace, if you like, into just units of 2 beads. And if Asprey's right, then you should only get 2 permutations. If Asprey's right and wool proteins are simply blue, red, blue, red, blue, red, if you break down those wool proteins into fragments containing only 2 amino acids, you should only get blue, red or red, blue. It's classic Karl Popper. You formulate a hypothesis and you try to falsify it, which is what Archer Martin did. And when Archer Martin put that to the test using partition chromatography, that is not what he found. And he presented that work at a meeting in 1946, a meeting of the Textile Institute in Leeds. And there's an interesting exchange between Asprey and Martin. So Martin says, in conclusion, the present author considers the structure of wool is more complicated than is suggested by Asprey. Asprey has looked at the structure of proteins constructively and with the eye of stoichiometric faith. Lacking this eye and approaching the problem analytically, the present author is unable to find the same degree of order. Now, Asprey's response is interesting. Asprey came back at Martin and said, Dr. Martin is such an outstanding experimentalist in the field of protein analysis. One cannot help feeling sad he should confess himself lacking in the eye of stoichiometric faith. This is an age of little faith, and it'd be a pity were the depression to spread to the proteins just when hopes were beginning to run so high. One thing we can be sure is that proteins are not a hodgepodge, but are constructed to ordered plans. Now, at first sight, that sounds as if Asprey's paying Martin a compliment, calling him an outstanding experimentalist. I don't actually think he was, and to understand why, I don't know if anyone recognizes these two characters here. So on the left, we have Dr. Sheldon Cooper, and on the right, his flatmate, Dr. Leonard Hofstadter from the hit sitcom Big Bang Theory. If you don't know it, I would stick my neck out and say this is one of the best and most successful pieces of science, communication, and popularization in recent years. Basically, Sheldon and Leonard are two postdoctoral fellows. They share a flat and they have a lot of adventures. It's a very funny show for many reasons, but one of the sources of humor and tension is Sheldon's innate snobbery towards Leonard, and that snobbery is rooted in the fact that Sheldon here is a theoretical scientist. He spends his day standing in front of a whiteboard, working his way through complex equations to do with string theory. Leonard, by contrast, is an experimentalist. He goes into the lab, he gets his hands dirty. And Sheldon looks down his nose at him. And I think that is what we're seeing here. I think we're seeing Asprey in the role of Sheldon, looking down his nose at guys like Martin and Singh, who sit in a former stable, billowing with chloroform fumes. Well, they had the last laugh, because they had done more. Martin and Singh had done much more than just invent a new analytical technique. They'd given birth to a concept, and it was one that came to be at the heart of molecular biology, because they'd realized you could use their method not just to analyze the different amino acids in a protein, you could use it to work out their linear order, or as they called it, sequence. Now, the problem they had was the wool proteins were too big. They needed something smaller, made of amino acids, to test that idea on. With the Second World War raging, they got that. It was an antibiotic, Soviet gramicidin, gramicidin S, and they then began what Singh called Martin's boastful undertaking to work out the complete order of amino acids in that. Helping them with that work were two names, both of whom went on to become two young scientists who went on to become massive names in the field of insulin. One was Dorothy Hodgkin, who, of course, in 1969, used X-ray crystallography to finally solve the 3D structure of insulin. The other, a young scientist called Fred Sanger. And Sanger realized that Martin and Singh's method might be used to determine the complete order of amino acids in a protein. And the protein he did that on was insulin. And after 10 years of hard work, he came up with the complete order, complete sequence of amino acids in insulin. Here's the original page from his lab book. That demolished once and for all that idea so beloved of Asprey, Bergman, and Niemann, that amino acids are arranged in nice, neat, regular patterns. They weren't. Of course, that raised the question, what does determine the order of those amino acid beads in the protein necklace? Well, today, of course, we know it's DNA. Back in the 1940s, the situation was very different. I think, thanks to films like Jurassic Park and the X-Men and Spider-Man, most people get today that DNA does something really important in biology. Back in the 1940s, it was thought to be a really boring molecule, just a monotonous repeat of the same 4 bases over and over again, the bases being those 4 different chemicals that make up the rungs of the DNA ladder. Most scientists thought it was proteins were the carriers of the genetic information. Someone who thought differently, however, was Erwin Chargaff here. He had a hunch that maybe what made species different was the amounts of 4 bases they had in their DNA. To put that to the test, he wanted to take DNA from different species, separate out the 4 bases and show that they varied. But his problem was a practical one. He had no means, there was no means of analyzing and separating those bases with enough accuracy and precision. Until, that is, Archer Martin came to Columbia and gave a seminar on the partition chromatography method that he and Richard Singh had developed in Leeds for the analysis of wool. And Chargaff realized he had exactly what he needed. So using partition chromatography, he took DNA from different bacterial species, sure enough found the amount of the 4 bases varied. It was the first hint at how DNA carries the genetic information. And those are the 2 pillars on which Genentech's success was built. Because Once you know the order of amino acids in human insulin, you can work backwards and deduce the order of bases in the DNA sequence that tells a cell how to make that insulin. The Genentech scientists did that, and then they synthesized base by base the coding fragment for human insulin and put it into a bacterium. What that enabled them to do, it gave them a head start it enabled them to overtake two eminent US academic labs who were busy also trying to get bacteria to make human insulin. And it allowed them to win the race. And that was a race that was severely hampered by regulations at the time, because the scientists were doing this work faced by an increasingly hostile media and public who were really terrified of genetic engineering technology. Now, because of that, the academic labs had to do their work in biosafety 4 category safety labs. So to give you some idea of that, you're talking moon suits, airlocks. They had to travel abroad to do it because there are no facilities in the US. Because the Genentech scientists synthesized their DNA, they were able to do it at the lab bench, and that's why they were able to beat the academic labs to it. Martin and Singh got their just rewards. In 1952, they were awarded a Nobel Prize in chemistry for partition chromatography, with this very memorable headline here: blobs win Nobel Prize for 2 young scientists. A plaque went up at Wyra to acknowledge that achievement. And to my absolute, it pains me to say this, but when Wyra moved from their site in Headingley out to the Ring Road in Leeds in 1980, I believe that that plaque ended up in a skip. Now, back in 2001, the Royal Society of Chemistry unveiled another plaque at the original Wyra site to Martin and Singh. That facility has since been turned into flats, so we don't think that plaque is there, but fear not. Martin and Singh haven't been forgotten, because in 2019, to celebrate their bicentenary of their founding, the Leeds Philosophical and Literary Society unveiled a brand new plaque to Martin and Singh right on that old gatepost that stands on the Otley Road in Leeds and is passed by 1,000-strong entourages of fancy dress-clad revellers heading down from the student area of Headingley for a night's debauchery and revelry in the city's flesh pots. And every time I see them going past it, I always hope that at least one of them is going to stop and have a look at that plaque and reflect on the great things that were done on that site. And there's just another photograph of it there. So I'm going to wrap up. What I think is great about this story is it illustrates the wonderful serendipity of science, right? You start with very practical, very economically oriented research into the nature of wool fibers, and you end up unraveling the chemical mysteries of insulin and getting the first hint at how DNA carries the genetic code. I think insulin has got another important lesson for us all, whether or not we're injecting ourselves with it, and it's this. When insulin was first injected into patients in the 1920s, the newspapers were full of these triumphalist headlines talking about this miracle cure for type 1 diabetes. The scientists, the doctors involved in the work knew it was nothing of the sort. They knew that what it did was it transformed a fatal condition into a long-term one that could be managed. But they were quite clear. You know, Elliot Jocelyn, he might have likened insulin to the vision of Ezekiel, but he said, look, this is a remedy for the wise and not the foolish. And after having had type 1 diabetes for 10 years, I think I know what he means. I can inject myself 4 times a day with insulin, and that will keep me alive. But for me to live well with diabetes requires me to do more. It requires me to behave responsibly on my part with regard to things like diet and exercise. And I think therein is maybe a lesson for us all about what technology can and can't do for us. I think there's very often a temptation to think that whatever challenges we face, be they AI, climate change, managing a global pandemic, technology will always do the heavy lifting. Well, it needs us. It's a partnership between technology and how we apply it. And I think that's as true for the management of insulin as it's going to be for dealing with climate change, AI, or future pandemics. Another final lesson, I guess, the past 2 years of the pandemic, we've all had a rough couple of years. With talk of PCR tests, mRNA vaccines, our numbers on our TV news every night, we've all become acutely aware of the importance of science in our lives. I think very often it's easy to get this idea that science is done by these geniuses who tower above us, above the ranks of us mere mortals shouting eureka. Blame it partly on Sir Isaac Newton and his line about, if I've seen further, it's by standing on the shoulders of giants. Although, again, to my shame, I learned only recently he'd actually nicked that from someone else. I think, staying with 18th century thinkers, I think there's someone else who gives us a much more honest account of how science really advances, and that is German philosopher Immanuel Kant, who said, out of the crooked timber of humanity, no straight thing was ever made. The story of insulin shows that, you know, insulin wasn't discovered by towering geniuses. It was discovered by crooked people. I don't mean they were criminal. I mean, they were flawed, complex human beings like the rest of us. Fred Banting was so depressed in March 1922, he was stealing alcohol from the lab. And he said, there was not one night during March 1922 I went to bed sober. It's done by crooked people. I think that is maybe what makes their achievement all the more impressive. And science doesn't weave this smooth upward path. It weaves a crooked winding path, as we've seen, from wool to insulin to DNA. And again, maybe that's what makes it so much more exciting. So I will wrap up there. I will thank you all for listening so patiently. I've just got a few acknowledgements here. A lot of archivists. I just want to thank Mr. David Allen, librarian of the Royal Society of Chemistry, for kindly fishing out some of Singh's papers. Professor Sally Smith-Hughes, the University of Berkeley, for helpful discussions on Genentech. The Leeds Phil and Lit Society for their kind support of a grant. My editor, Sonka Adlum, and Jessica Jones in publicity at OUP. Professor Pierre Lefebvre of the International Diabetes Federation. Natalia Rattan and all the archivists at the University of Toronto, invaluable for their help with Banting and Best papers. And Dr. Adam Green and all the staff at Trinity College, Cambridge, for fishing out endless boxes of Richard Singh's papers. And on that note, I will thank you all very much and wrap up there. Thank you.
Can you hear me? Oh,
yeah, I can hear you now, Peter. I've got you now. Yeah, yeah.
Sorry, I think I was on mute. I'm sorry about that. I was just saying it was a fascinating talk, and it was amazing how you could bring the Rosetta mission into the whole thing. So, sorry, I didn't realise I was on mute. Okay, Kirsten, we have a couple of questions here. One is from Henry Rexper, asking what was the contribution of Pauling to protein chemistry? I mean, of course, he came up with the alpha helix, didn't he?
Oh yeah, Pauling, massive contribution. Yeah, because I mean, he was able to work out the configuration of the peptide bond, I think, and then yeah, he came up with the alpha helix. So I mean, he's a man who had his finger in many pies. In fact, actually, he was probably so focused on doing the alpha helix. He did actually say this in a sense. He said he reckoned that's why he never cracked the DNA structure, because he was so. I think he felt his attention was split. He was serving at two masters between the DNA helix and the alpha helix, and I remember detecting a certain note of regret, I think, in his reflection on that. But yeah, you know, the alpha helix isn't bad, is it? You know, so another one like Fred Sanger, who got 2 Nobel Prizes, I think.
Yeah, we actually had a triple. Pauling, of course, came up with the triple helix model for the DNA. And we actually had a model of it in the Science Museum, and shortly after I took over from the Science, curator of the Science Museum, it fell apart. It fell apart through plastic fatigue. So well, that was the end of that.
You know, I always think about Pauling and DNA. I mean, what Pauling desperately needed access to was good quality X-ray diffraction pictures of DNA.
This is the whole story.
There's a wonderful what if here, because I mentioned William Astbury. So I guess everyone knows about Rosalind Franklin and Raymond Gosling's famous photo 51 picture, where it shows the cross pattern of spots that told James Watson this molecule is coiled into a helix. I mean, there's a plaque outside King's in London now says that photograph's one of the most important ones in the world. What few people realise is a year earlier, Asprey here at Leeds and his research assistant Alwyn Beaton had taken an identical picture. I've seen it. And he never did anything with it. I mean, it's the irony. James Watson said, Rosalind Franklin's picture made my mouth fall open and my pulse race. Asprey's reaction couldn't have been more different. He never did anything with this photograph. He never presented it at a meeting. He never published it. He filed it away. And around that time, he was visited at his home in Headingley by Pauling because they were good mates. And you just wonder what would have happened if, as they sat by the fire, sipping whiskey, as I'm sure they were at Asprey's house in Headingley, if he'd have turned to Pauling and said, hey, you want to have a look at this interesting photograph of DNA that my guy Beaton's taken? I think Pauling would have gone back to Pasadena with fire in his belly.
The other question we've had is, Alan Johnfield asked you to explain the meaning of the title of your other book, The Man in the Monkey Nut Coat. Why the Man in the Monkey Nut Coat?
Why that title? Right, that's a good question. Right, so I've just talked briefly there about Asprey and DNA, because it was actually the very first attempt to crack the structure of DNA using X-rays was done in Asprey's lab by Florence Bell, who for me is the other unsung heroine of DNA. But, it'd be easy to sort of think of Asprey as being like, oh, there has been in the story of DNA. What I like to remember him for was his big idea was that living systems are made of these huge, big, long chain molecules. And those chain molecules can do something interesting. They can change shape. Now, that explained why wool fibers are stretchy, because the chains can be stretched out. But I mean, today it explains how hemoglobin can carry oxygen. It explains how the spike protein on the surface of the SARS-CoV-2 virus can bind to a human cell and get the virus in there. But Asprey had this idea that, we could not only study the structure of these big, long chain molecules, what if we could actually deliberately alter their shape for our own ends? And he had this idea that if you took the main protein from monkey nuts, or peanuts as we know them, and monkey nut proteins, the protein chain is coiled up into a ball. He had this idea, what if by chemical treatment you unravel the coiling of that ball and you refold it into a long insoluble fiber that could then be used as a substitute, a cheap and abundant substitute for wool in the textile industry. And the company ICI loved this idea so much, they built a pilot production plant at Ardere in Scotland, and they started making a textile fibre from monkey nut proteins. They called it Ardil. And they actually wove Asprey a complete overcoat out of this Ardil stuff. Now, it didn't turn out to be the salvation of the British textile industry. There are no spoilers there. There are letters in which Asprey's complaining, saying the coat's falling to bits. But I just thought it's a great story because it illustrates his idea that it's all about understanding the shape of these proteins. And today we can see the importance of that, as I say, with the spike protein on SARS-CoV-2. It's also it's titled a little bit of a play on the classic old Ealing Alec Guinness film, Man in the White Suit. Because if you know it, Alec Guinness is this idealistic young scientist who thinks he's invented this revolutionary new textile fibre. And in a sense, I thought Asprey was almost a case of life mirrors art.
Hamdid just asked the question, how did Pauling work out the sequences of insulin along with the sulfur bridges?
Yeah, so he's got a later paper when he works out the disulfide bridges. So he gets the sequence first. Then later on, he starts identifying the specific cysteine or methionine residues, I think, weren't it? Involved in, my biochemical knowledge is straining.
Talking about Sanger, by the way, I'm not quite
sure. Sanger, yeah, sure. Yeah.
Okay, there's a comment here rather than so much a question, but it was somebody, Alan Crooks had commented on the chat that if there was a problem in the laboratory, Archer Martin could think of 3 solutions by the time he walked across the laboratory.
Really?
Possibly.
He was
possibly an apocryphal story, but I mean the thing. I mean, you've read my biography.
Yeah, Odium. Yeah.
And the trouble with Martin was it wasn't so much his ability to think of solutions, it was more his inability to realize whether it was an appropriate solution or not. I mean, a case in point being his invention of a tornado machine. When he was in America, he came up with a machine to make tornadoes. And James Lovelock said to him, "Well, that's a wonderful idea, Archer, but why would anybody want to do that?"
Yeah.
And that was his problem. He didn't have a very strong grasp on reality altogether, really. But there we are.
Yeah, I mean, he seems to have become quite a tragic figure in his later life. Become really kind of isolated as he set up his own consultancy, didn't he? And he didn't seem to stay connected with what was going on in science. I've always wondered, what was his response to developments such as, the growth of molecular biology and genetic engineering. And he just seems to have been completely more and more kind of out there in the wilderness, out on his own.
He started working on chemicals in potato skin.
Yeah. And so you've got this really tragic image of this guy just surrounded on his own in this lab, surrounded by rotting potato skins. It's
well, he was definitely an obsessive, yeah. Okay, well, thank you very much, Kersten. That was a wonderful talk. We've had lots of good comments on chat. Thank you so much for coming to talk to us. It's entirely appropriate. Wonderful for the insulin anniversary, even though there is some debate about what date we should be celebrating.
Well, yeah,
and whom we should be celebrating. But thank you once again. We had over 60 people watching, so we hope you all come back to our next talk, which will be next month, 3rd Tuesday, and it will be given by the American scientist, American historian of science, Mary Virginia Orner, who will be talking about elements predicted by Mendeleev and what happens next. So we've had a wonderful today, and we hope to have another wonderful talk next month. So please join us again. Thank you very much, everybody. And thank you very much, Kirsten.
Thank you very much. Take care now. Bye now.